Hello everyone and welcome to another MoTeC webinar. My name is Mark McCoy and we are going to be continuing with our M1 training. Hopefully by now everyone has watched our M1 training videos on the introduction to M1 Tune. M1 Tune being the program we use to configure the ECU and do our tuning on the dyno. Today's particular subject will be based on the initial setup workbooks. The first worksheet we will be looking at is the engine details worksheet. So what I'm going to do now is move over to my M1 Tune software. At the moment I'm offline. I'm not talking to any ECU, so therefore there's not really much going on. If I go over to my quick launch tab, I'm going to choose my webinar ECU, the one I'll be using for today, which is using our general purpose or GP package, and we'll just open this up. So what I'm going to do, like I said, we're going to be using our initial setup workbook, so I'm going to go to that one, and the page we're talking about today or worksheet is the engine details worksheet. This worksheet uses or contains the basic elements for how we're going to run this engine, or more or less the parameters the ECU needs to know to understand what engine it's running. As we've mentioned in previous webinars, this ECU package is completely based on more like an efficiency model of the engine, so how much air the engine can get in and out. So there's quite a few details that the ECU needs to understand about the engine. There's also a couple of parameters on here which we need to mention. That's probably a good idea to have them set up right at the beginning. So this engine details sheet is the first one in the initial setup. The idea is that we're going to go through each and every worksheet in the initial setup. So I'm going to do a webinar per worksheet. So okay. The first parameter we're talking about up the top here is engine run threshold. Now that's an RPM figure that decides whether the engine is in a running condition or a cranking condition. So by cranking, what we're going to be doing is the engine's on the starter motor. It hasn't fired into life yet, so that's going to mean the fuel compensations are a little bit different. So we're going to be using a cranking compensation to add fuel when it's cold and cranking. As soon as it goes above this 300 RPM, the ECU is going to know to switch over to post-start and running conditions. Now that will really depend on what type of engine you have, what the starter motor is, etc. So it might take some experimentation, but the idea here is the engine I'm using in this example cranks at about 220 RPM. As it fires into life, it quickly races past 300 RPM to its idle of about 800. So 300 is probably not a bad figure for this. So, but you can change this depending on what your engine actually does. The next one is the engine displacement. As I said before, this is an efficiency model, so realistically the ECU has to understand how big the engine is in swept displacement. So I've got here 2.7 litres. Quite simple, you should be able to work out how big your engine is. The next one is an engine efficiency mode. Now this quite simply, the easiest way to describe this is, are we doing a manifold pressure based tune or are we doing a throttle position based tune? It's quite easy way to sort of discern between the two. So in this case my engine has been tuned on a manifold pressure sensor, so I've set the efficiency mode as manifold air density. Now if I was to do a throttle position based engine, what the better idea is to do is use an ambient air pressure density to more or less scale how much air is going into this engine based on throttle position. Now realistically this mode would assume that you have an ambient or barometric pressure sensor connected to the engine. If you don't, you would have to make sure that your ambient pressure default setting, which we'll get into in another webinar, is set correctly or relevant to your area or what your barometric pressure or ambient pressure is. So quite important to make sure that one's correct. I'm going to leave that back as manifold air density. Next, how many cylinders? It's pretty self-explanatory. The ECU wants to know how big each individual cylinder out of that 2.7 litre is. So mine's a 4-cylinder. Simply put in 4. If you're using an M150 ECU, you'll be up to 12 cylinders. The engine charge cooling gain. This is a parameter which basically gives the ECU an idea of the cooling effect that the fuel vapor has when the fuel is injected into the engine. Everyone sort of understands if you spill a bit of petrol on the back of your hand feels cold. So what that effect is as the fuel vaporizes, it takes energy out of your hand, makes it feel cold. This charge cooling gain is something that's quite important to the tuning of the engine and should really be set before you get into the major tuning part on the dyno. There will be a webinar specifically for this charge cooling gain. On my engine I've tuned it and it works out at about 13.5. So for an initial startup, 13.5 is probably the way to go. You can just leave that at whatever default comes in your particular package, but I would highly recommend watching the future webinar on the charge cooling tuning because it is quite important. Next parameter is the engine load normalized mode. Now what this sets is what is the scale or what is the parameters we're using for the y-axis of our ignition table. Obviously the x-axis is in RPM, the y-axis is in engine load normalized. Now what we're talking about with these three settings is, if I go to normal to start with, normal simply sets or tells the ECU that we're going to be based on manifold pressure, and we're going to also compare this manifold pressure to a standard temperature and pressure conditions. Now it does assume that we have a inlet manifold temperature sensor, so that's a temperature sensor located on the plenum side of the throttle body. So that's when you would set like the normal conditions if you've got those sensors in place. If you don't have the intake manifold temperature sensor, what I would suggest is setting the engine load normalized mode to inlet manifold pressure, and what this does is it more or less takes out the standard temperature part of the calculation. Next option is throttle position, and let's say we just want to map this engine purely on throttle position. More or less what we're doing here is just saying, instead of trying to calculate a specific load, just whatever the throttle position is, use that as the number on the engine load normalized axis of the ignition table. It won't actually change the name, so by changing this parameter here, don't expect the ignition table to suddenly have a different label on it. This just sort of connects where that engine load normalized axis comes from. So in this case it'd be throttle position. Our engine load average time constant. Probably a good example here would be something like 20 seconds. So I'm just going to change that from the default of 1. What this sets is we've got an engine load average channel. Now it basically says how hard are we using this engine. So if we had something like a circuit car where we're spending a lot of time on 100% throttle, you can imagine that the engine's being used under high load a lot more than say an engine that's been driven around the street. So what we're saying here is if we filter that engine load channel, we get like a more or less an average, and we can then use that as a more or less a fuel compensation. So if you're spending a lot of time at full throttle, if the engine load average is fairly high, what we could do is maybe pull some timing out, put some fuel in based on how hard we are using this engine. There's probably going to be a future webinar mentioning this in our tuning, but as an average idea, something like 10-20 seconds, generally like maybe the lower number would suit an engine that's being used at higher loads more constantly than an engine that's being used at lower loads constantly. Again, back to the whole efficiency model type tuning of this ECU. The ECU needs to know what type of fuel you're using, so it needs to know some details about the fuel. And this, quite simply to start with, is the stoichiometric ratio of the fuel, like what is the air-fuel ratio. Now you can see over to the right there's a number of different options. So if you're using your methanol or your E85, you need to enter the correct number here, because once the ECU works out how much air is coming in the engine based on our efficiency tuning, it will calculate based on, like, our aim lambda, how much fuel to throw in. So obviously if it needs to work out how much fuel, it needs to know the stoichiometric ratio of the fuel you're using. So quite an important parameter to fill out. Same as the density. So this is more or less how many kilograms per cubic meter the fuel more or less weighs. So what we do is we put in the density as well. This can change depending on fuels as well. So if you're purchasing like a race type fuel, generally what will happen is it will come with a data sheet which gives you all of these parameters, or all of these factors based on the fuel that you're buying. Another one would be the temperature coefficient. So as we heat and cool the fuel, the density of that fuel is going to change. Now if you have a fuel temperature sensor, the ECU will automatically compensate the density of your fuel based on how hot or cold it is. So probably a good idea to make sure you have the temperature coefficient as well. As more information about different fuels comes to hand, we might even update the help screens to reflect that. But like I said, if you're buying from a specific supplier, it's probably a good idea to get the data sheet for the fuel you're buying. Injector location, quite simply, do we have the injectors before the throttle body or after the throttle body? So after the throttle body would be in the plenum, sort of like a standard type engine up near the cylinder head. Before the throttle body would be something like maybe a V8 touring car, where they've got the injectors a long way out of the inlet runner trumpets. Okay, this parameter is quite important as well, because it depends on how the fuel pressure or pressure drop across the injector is calculated. So if you have an injector in the plenum, it's going to be affected a lot by the manifold pressure, whether I've got boost or vacuum. If it's on the outside, like in the touring car, it's only really affected by the atmospheric pressure or the airbox pressure. So they're two different sort of ways of working out the pressure drop of fuel across that injector. It's quite important to get that right as well, and should be fairly easy to work out. For inlet manifold pressure mode, we've got like a few different ways of doing it. The automatic mode would suggest that we have an actual manifold pressure sensor. Now the reason it's called automatic is more or less we default to using the sensor. If the sensor is in error, what it will do, it will go to a inlet manifold pressure estimate table. Now this is a table I've calculated from the engine I'm using. It quite literally says at a certain RPM and a certain throttle position, what is the manifold pressure. Okay, so what we can have with the automatic inlet manifold pressure mode is just say, well, use the sensor unless it dies or it becomes faulty or the ECU decides that it's not reliable, then go back to using the inlet pressure estimate. Okay, now I could set it to purely use the sensor, which will mean if I have the sensor go into fault, all it's going to do is revert to the sensor's default reading, which is only one fixed number. Probably not the best way to go, and not really the recommended. The automatic mode is pretty good, but it means that you really need to have filled out that estimate. If I just put it purely on an estimate mode, what it's going to do is simply reference that estimate table. So it's not going to use a manifold pressure sensor. It's simply going to look at the throttle position, and then based on your table, it is quite simply going to pick a manifold pressure that is represented by your throttle position and RPM, and use that manifold pressure as the y-axis site for your main fuel tuning. The main fuel tuning map is always in manifold pressure, and this manifold pressure mode simply tells the ECU where does it get the information to use that axis, either from an estimate, automatically from a sensor, or just a straight sensor. Now, this inlet manifold pressure estimate table, realistically, if you're doing a throttle based tune, you may not need the entire table. So if you want to simply make that a simple table, if we press A for axis, I can get the engine speed and simply turn that off, and then make just a simple table based on my throttle position and what I reckon the manifold pressure is going to be. I could even make that quite simply a straight line. One thing I will get people to note is at 0% throttle, it's very unlikely to have 0 kPa of manifold pressure. So if you've got a rough idea of what manifold pressure the engine should idle at, for a good 4-valve engine about 30 kPa is probably ideal. So you can see that I've started this table at 30 kPa and then sort of gone up. You could probably straighten that out depending on the engine or how you want to tune it, but as people who've done work with butterfly throttle bodies before, you'll understand that the relationship between angle and flow is quite non-linear, so there's a bit of a curve in it anyway, but completely up to you. Another parameter we have here is a throttle area parameter, or table, sorry. Now what this does is this is only really used when we're using electronic throttles or drive-by-wire, which is a lot more common these days. What we're basically saying here is giving the ECU an idea of, if I've requested a throttle position on the electronic throttle body, how much area is open, so more or less what percentage of the potential flow of this throttle body is available. So when we get to our drive-by-wire setup, when you move your pedal, what you're actually requesting is a throttle area, not necessarily just a straight percentage. So this is the way to sort of translate what you're requesting into something that's roughly related to the flow of the throttle body. So quite important. This will be a default table, as you can see here. This is what will come in most of the packages, so probably just leave it as it is. Moving on to the second calibrate element on this page. This one's quite simple. What we're doing here is we're setting the top dead centers and the bank assignment for each cylinder. So what you'll notice here is I've put in the degrees or top dead centers of each of the cylinders of my 4-cylinder engine, and I've done it actually in firing order. So cylinder 3 is the second one to fire, cylinder 4 is the third, cylinder 2 is the last one to fire. Now it does assume that cylinder 1 is 0 degrees top dead center. That's just the way we have always referenced our engines. Also, you can see, being a 4-cylinder inline engine, all my cylinders are on bank 1. The bank stuff specifies which bank. Maybe I've got a V engine, whether the cylinder is on bank 1 or bank 2. Now this sort of really comes into play when we're talking about bank to bank compensations for fuel based on closed loop, and also knock control. So always a good idea to make sure this information is correct for your engine. Okay, thank you for watching this first in the series of initial setup worksheet webinars. If you would like to see more of our webinars on the M1 system, you can go to MoTeC.com and search for our webinars, or you could go straight to YouTube where all of these webinars end up. Let's say you have some other questions and maybe it's out of office hours, you can always join our MoTeC forum as well. So there's plenty of people around the world who are awake at different times. Put a question up on there, and you know, you're open up to a lot more people that way. Okay, thanks for watching.